Hey guys, welcome to class. Today we're going to be talking about the Cantor diagonal argument, and I'm Rebecca Lang. And then at the end of class, we'll also be talking about a project that you guys will be doing on your own. To begin, let's talk a little bit about what the Cantor diagonal argument is. We talked a lot about who Cantor is in general throughout this book by Rudin, but it doesn't necessarily talk a ton about what the diagonal argument is. So I think it's important to have a solid foundation of that before you guys move into your project. So George Cantor, famous mathematician, he did a lot kind of with set theory and talking about uncountability, real numbers, things of that nature. And in 1895, he published his Cantor's diagonal argument, which ended up helping us prove, or actually was the proof, that the real numbers are uncountable. And the way he did this is he was able to prove that there's no bijection between the natural numbers and the real numbers, which is definition of countability. And in doing so, he didn't use all of the real numbers. He only used an interval from 0 to 1. But that interval from 0 to 1 had the same cardinality as all of the reals. And just in that interval, he was able to prove that there are more numbers in that interval than there are in the naturals, and that there is no bijection because it's not on 2. And he used this using a very interesting proof technique that's actually named after him because of he was the first one that used it. And so to start, recall that the definition of countability is that you can have this bijection of whatever set you're using, we're calling it S in this case, to the natural number. So there's this bijection happening. So we are supposing that it's countable, that the real numbers are countable, even the real numbers on this interval are countable, and that there is this bijection from the natural numbers to this real numbers in the interval. And then he creates like a chart. So this is a great way to visualize it, is like create a chart, use these different real numbers to go in that chart. So these are just like random real numbers. You could be more precise if you wanted to. And look at the diagonal that occurs here. So from there, if we added 1 to each of the values of those diagonals, so we see the diagonal here, it's 3, 7, 2, 1, 0. If we added 1 to 3, we would get 4. Kept going, we get 0.48321. And what we see happening is if I add 1 to every single one of these points in this diagonal, it's not going to be the same as any number I already have. It's different from the first number in the first spot. It's different from the second number in the second spot. It's different from the third, so on and so forth. So it's a completely new number. It's not already in this chart. And so this chart is mapping natural numbers to different real numbers. But by doing this, we're creating a new number that's unique, that's not already in this chart. And since real numbers or decimal expansion is unique, it's not like this is just another way to write the same number that we already have. It's a completely new number. But it is still an element of the reals, right? It's still it's not imaginary, it still fits into the reals. And so what we see is that there's a contradiction here because it's not on 2. Not every single natural number is mapping to one of these real numbers. There's actually this real number that's been uncounted for, and there's actually a lot of them that are uncounted for. You know, you could take the next diagonal and do the same thing and change any of the numbers in the first one too and whatnot. It would still create something that's completely new you haven't seen before. And so this shows that the real numbers are not countable. In fact, they are uncountable. There are a lot of implications to this. It also applies to the power sets. So if S in this case is the set 1, 3, and 4, so contains those values, the power set, which we've talked about more in like linear algebra, not so much in this class, would be like 0, 1, 3, 4, the set containing 1 and 3, the set containing 1 and 4, so on and so forth. So you can see how this is created from the S. And then there was already a connection that was found. If it was finite, you would take 2, raise it to the cardinality of S, and that would be the cardinality of the power set of S. So there's 3 values here. So the cardinality of S is 3. 2 to the third is 8. Well, there's also 8 values here. So the cardinality of P of S is also 8. And the same does not necessarily apply if it's infinite. But we have proved with Cantor's diagonal argument that the cardinality of S is always going to be less than the cardinality of P of S. And then many other people have expanded on his work. We're going to talk about more of those applications moving forward. But like I said, he was very foundational in set theory, and specifically the axiomatization of set theory, which allows us to do a lot of the things we do with set theory today. And yeah, his work is used for the rational numbers as well. Before he proved that the real numbers were uncountable, he helped prove that the rational numbers are countable, and has done a lot of other work. Is almost most famous for the Cantor set, which we've seen a lot of his work on that in our class as well. And we'll do more with that moving forward here too. He also, this is a proof from Rudin, he also proved that the binary representation of real numbers is uncountable. So use sequences in a similar diagonal argument in order to do that, which is unique. And we'll look at this in an example I have moving forward. And then some of the application, he did a lot. Like I said, set theory was a big aspect that was impacted by him. So talking about hierarchy of infinities, some infinities are bigger than others. Even recognizing, okay, real numbers are uncountable, but the natural numbers are countable, but they're both infinity. What does that mean? He also helped discover the descriptive set theory, which shows like non-existence of different functions. Used a lot in in logic and incompleteness. Gödel used this diagonal argument. It's now a proof technique, and so Cantor was one of the first ones to use it, so that's why it's named after him. But it's a proof technique that many mathematicians have used. So a lot of these are mentioned because they use that same technique in doing so. And so Gödel's first incompleteness theorem is talking a lot about like truth and proving that things are true and that some things just can't be proven, but they are true and things of that nature. And so Tarski's undefinability of truth theorem kind of builds on that and just saying like, hey, we can't prove something that's true, especially in just one mathematical equation. So interesting things to look at. Also, his work is used in functions, both in showing that some functions grow faster than others and also showing the utterly discontinuous functions. And then lastly, it's used a lot in like recursive and enumerable sets, which you kind of saw his proof of the binary used that idea of like a recursive set. Okay, getting into the project, I know that's what you guys have been waiting for. I wanted you to have a solid foundation of Cantor and that diagonal argument before we start on the project, because you will be using this diagonal argument twice in theory in proving something, and then a third time in MATLAB in applying it. So it's really important that you have a solid foundation of what it is. And I didn't feel like we saw a lot of it in the book in some of our assignments. So it's important that you recognize how to use it before we move forward. So the first thing I'm going to have you do is prove the Cantor set is uncountable. So this is just like typical Cantor set. You guys have seen this before. You have the interval from 0 to 1. We're taking out that middle 1/3. We're going to continue to do so. And then that Cantor set is going to be the union of all of those little intervals that we have created. As we're looking at like n going to infinity, and we have so many of these little intervals that have very little inside of them. Cantor set is super interesting. There's a lot of unique things that happen with it that don't necessarily happen even in sets very similar to it. So you'll prove that it's uncountable. The book has some great resources to use in proving that. And then one big thing I want you to do is use the diagonal argument. The book lays out a very similar proof, not using the diagonal argument. It's not to prove that the Cantor set is uncountable. It was more to talk about that the Cantor set is perfect. But use the diagonal argument. That's what it's all about. Okay. So that's the first thing I'll have you do. I have an example of a diagonal argument moving forward on the next slide, which I'll show you. which might help you think about how you can do that. Okay. In addition to that, I want you to look at the properties of the Cantor set. This is more for part 2 of the project, so there's 3 parts to your project. First is just proving general Cantor set it's uncountable. The second part has you actually create one and do some comparison, but before you can compare, you have to know some things about the Cantor set. So Cantor set's closed. That means every limit point is converging within the Cantor set, or is an element of the Cantor set. That's a better way to say it. It's bounded. So it's bounded 0 and 1, right? It's in the interval from 0 to 1. That's kind of a given. It's compact. So remember, if it's closed and bounded, it's compact. It's perfect. There's a great proof in the book. All of these are different. This is where you can find this information in the book. So please reference that as you go through. So it's perfect. That proof is really interesting, worth looking at. It's uncountable. So it states it. There's not a specific proof to prove that it's uncountable in the book, so you can look at that, but prove it yourself. It's nowhere dense. So these next two are very unique to the Cantor set. They do occur in other places, of course, but they are more interesting. So it's nowhere dense, meaning nowhere within the Cantor set it's dense, and that's because there's basically like between each value there's like this gap. And then similarly, this one is arguably the coolest property of the Cantor set, is that it's measurably 0. So as it takes the union of all of these little sets, it gets 0 because there's basically nothing remaining, which is so interesting. But I don't want to get into it. But think about it. Take a second. Okay. Part 2. You're going to construct an uncountable subset of the reals in the interval 0 to 1. So not every interval in the reals from 0 to 1 is uncountable. So just keep that in mind as you're doing it. I'll just give you an example. If instead of taking out the middle 1/3, let's say you took out the left 1/3 and the right 1/3 each time. So instead of getting 2 sets after the first step, you would just have one interval that would go from 1/3 to 2/3. You do it again, you'd have another interval that's going from, I don't know, so the ninths to something else ninths. And it's getting smaller and smaller, and it's combining to be one number. So that's not going to be uncountable. You're actually going to end up with the mean. Okay? You're just taking the average. So don't do that. Instead, find something that's uncountable. So think about how you can manipulate the Cantor set to give you something new. There's a lot of ways you can do it. So once you find your new set, make sure it's uncountable. If you're not sure if it's uncountable, that's fine. You got to prove it anyways. So in the proof, you'll figure out if you did it right or not. And then state the properties that is shared with the Cantor set. So I'm giving you an example just so you can kind of see how to use this. I kind of did a little more of an interesting example. So I did the binary representation from the interval 0 to 1 with a restriction. Because if I just did the binary representation on the interval of 0 to 1, that's just the binary representations of the reals. It's basically just the interval from 0 to 1, just mod 2 instead of mod 10. So that's why there needed to be the restriction aspect of it. So the restriction you can kind of see at the end here is that every other term is going to be 0. So every even term is. And we're looking at the decimal expansion. So when you're using that diagonal argument there, look at the decimal expansion. I suppose I didn't actually have you solve this using the diagonal argument. You definitely could have. I kind of just shortcut solving method because Rudin had some great theorems that I was able to use to make this proof super fast. So one of the theorems, 2.43, is saying the real numbers from the interval 0 to 1 is is uncountable. So every interval of the reals is uncountable. Okay, so I'm still using an interval of the reals, so that part's going to be uncountable. Okay, our binary representation is uncountable. Yes, I showed you that proof already. So the binary is uncountable as well. So boom, B is uncountable. That was a quick one. Try to use the diagonal method if you want. I think that would be a cooler proof. All right, binary representation is bounded. So since I'm having you use the specific interval from 0 to 1, all of them should be bounded. So that's a given. Uncountable, also it has to be uncountable in order for you to use this as a problem. So those are what it shares with the Cantor set. It's both bounded and it's uncountable, but it differs from the Cantor set in every other aspect. Not every one of your intervals they're going to have these same shared properties as mine did. A lot of actually other options that you could do would still be closed. It might still be compact. It might still be, some of these other things. They're not going to share everything with the Cantor set because specifically that measurably 0 is like super unique to the Cantor set. But it'll share, maybe more than just the two. Okay, so because I had that restriction that's kind of causing it to jump, it's not going to be closed. So some of the limit points aren't going to fall into that. And if it's not closed, so a lot of things follow from it being closed. If it's going to be closed and bounded, I would know it's compact. So since it's not closed, it's not compact. It's also not perfect. Closure is like it needs to be closed in order to be perfect. It's also not nowhere dense, so that's an interesting concept, that nowhere density, because I have that jumping once again, there is points where it would be dense. So it's not nowhere dense. It's also not dense. So it's like in this in between. And then lastly, similarly, like I talked about, since I'm skipping, it's not measurably 0. Also, this nowhere dense concept is connected to the closure as well. It's not like quite as connected as something like perfect or compact would be, but that can help you see that too. Okay, so for the fun part, we're going to use MATLAB. With it, MATLAB, we're going to use it to detect error. So one way that this Cantor set and this Cantor diagonal argument are still used in our world today is in the world of computer science. And it's used to detect error. It's used to eliminate noise. It's used to compress data and a lot of other things. So really interesting to see how not just math has grown from what Cantor has done, but we are still using what he has done in our day-to-day life, whether or not you know it. Your computer is doing a lot of those things behind the scenes. So with that being said, for the MATLAB portion, we are all going to be using the same study. So I have a study of over 10,000 participants. I found it online. I did not interview 10,000 people about sleep. So how many hours they slept, how many hours they studied, and how successful they were on the exam. So we are going to look at those and do some things with MATLAB to compress that data, compile it, and compare it using this diagonal argument. Before you do anything, you have to download this Excel file. So click the Excel link before you click the MATLAB link. Should have probably flipped them. And that Excel link is going to take you to this document. It will not work in MATLAB unless you save this document to your device. So this is the document it will open to. It's called sleep_study. Save it to that name, sleep_study. You don't need to do anything to the document itself. You just need to save it. And the reason why is like after you have saved it, I'll just go back to the PowerPoint. After you've saved it, then you can open your MATLAB. And the first thing that MATLAB is telling this document to do is to read the document sleep_study. So if you don't have the document sleep_study saved to your device, MATLAB is just trying to read a file that doesn't exist. So you have to save it first. Once you save it, we'll move forward. So there are 2 independent variables and 1 dependent variable in this case, because there is the amount of hours that this person studied, and there's also the amount of hours that this person slept, and both of those things are going to affect their performance on their test. So it's taking both of those into consideration, and then it's going to output this performance index. These names are the same that they are in this Excel file, performance index, hours studied, sleep hours, okay? So they have to be the same for it to read it correctly. Okay. We are creating kind of like a matrix using both of my independent variables, and what these things are, or what these few lines of code are doing is it's creating an equation that's going to help predict it. So we are trying to linearize, we're actually creating systems of linear equations, but linearize the data into some equations. So that way, let's say I try it on the 10,001th person. Okay, what's going to happen? So that's what's happening here. It's helping me predict my data. So I'm creating a new equation that's going to be predicting it, and I'm using the old equation, kind of what was given in the document, and that is what we are comparing here. So we are creating two separate documentations, and we're going to compare those. Okay, so what we have happening is we're creating a matrix, one that has both the independent variables and the initial dependent variable, which is how many hours I slept, and another with same independent variables. My dependent variable is now going to be I predicted they do. So this is Y is their actual score on the test, and the Y predict is what I predict them to get on the test. So what we have done is we've created two different matrices, and they're actually have three columns. And then what this next thing does is we need them to be square, because if we're trying to look at the diagonal to use this diagonal argument, they have to be square matrices. So like we talked about, this was a massive data set, right? There was 10,000 different people in the initial data set. So we are compiling them into a 3x3 matrix. So that's what this minimization does. This is going to tell me what the diagonal is. And then we are comparing them and seeing how much error there is. So this is kind of like my error amount. So I'm saying, okay, my error should be less than 0.05%. Or sorry, 0.05. 5%. And then we are comparing the two. What we see kind of more down here is we're creating a comparison table, comparing the two, and then it's also going to tell me how much error there is based on, okay, how did the predicted Y compared to what they actually got. Okay, and then you run the data set, and what you can see is that they studied 7 hours, slept 9 hours. They were predicted to get a 73, so there might have been some error in the equation that we created, but they actually got a 91, so there's 17% error there. Okay, and then similarly, if they didn't sleep super well, they didn't study a lot, they were predicted to get a 36, but they actually earned a 65, so they did better than what was expected. And then this one was kind of like a interesting one. If they got a decent amount of sleep, got a decent amount of study, they were predicted to get a 68, but they actually got a 45. So that one was interesting as well. And so then write a little bit about it. I had said, there's some error probably in our problem, right? I took a massive document. I'm trying to compress it into a 3x3 matrix. This is something we are doing in this case because that higher math isn't necessarily something you would see at the undergrad, early on levels, or in a high school. And so we are compressing it to a 3x3 matrix because that's something we're comfortable with and we're able to use, but it's not necessarily going to give me the most accurate. And similarly, the equation, those linear equations that we use to try to predict, also had some error, right? We're trying to predict human behavior. That's a hard thing to predict, as many people have found. And there's a lot of other things that could affect. It's not like this is a closed lab and the only thing that's going to affect them is how much they sleep and how much they study. There's a lot of other things that are at play when we're dealing with humans. So interesting to look at. What you're gonna do is actually a little bit different though. So this is a test one that you can look at. What you will do is that is different is you're actually going to do this twice. So we saw how both sleep and studying affect test scores. Now what I want you to do is to just look at how sleep affects test scores first. So, or study, let's do study first because that's X1. So you would, get rid of your X2 for a little bit, or maybe don't delete it up there, just like delete it here. And then just use X1. You'd have to edit some of these, so on and so forth. Run it through. Very similar process. There's a few things that you'll have to change, but it's not like a crazy amount that's different. And you'll see, okay, based off of how much they sleep, this is how they should score. Or how much they study, this is how they should score. Then you would go back and then you would maybe get rid of the X1. So if you want to do this in the same document, you would probably copy and paste it and also change the name of your A to something else so it's not using the same data. But yeah, you get rid of your X1 and you just compare the sleep. Okay, if they slept, what would happen? So on and so forth. Just slightly making some edits to names here. You're not doing anything crazy. Running the data. So we're going to run it twice. When you run it twice, you're going to get two equations, or sorry, not two separate tables. Because you're taking out one of those rows instead of a 3x3 matrix, you're creating two 2x2 matrices. And you'll look at and you'll compare them. So let's say row 1 is talking about if you got 8 hours of studying, you're predicted to get a 91 or whatever. You got 8 hours of sleep, you're predicted to get a 91. Okay, but if you got 8 hours of studying, you actually got a 97, you got 8 hours of sleep, and you actually got a, I don't know, 82. The next question is, which is more valuable? Well, in that case, studying is more valuable than sleeping because you got the same hours of studying and sleep, but you actually scored higher by getting more studying than sleep, right? Maybe they're the same, then you would say sleep and studying are both super important. Maybe you'll see that sleep is going to give you higher scores than studying will. So look at that, write a little bit about why you think that's happening. Also, you can kind of see here, I wrote a little bit, and I also wrote a little bit in the project. I'll show you the next couple pages. There's some error. Why is this not perfect? Stuff like that. Okay, back to the PowerPoint. Let's just finish up real quick. So, I think if I press this button, it's going to go back to the Okay, so looking at MATLAB, we talked about the first page, second page. I explained this already. This is what you will be doing in the project. So remember, you're using the same data twice. You're getting two different tables out of it. And then you'll talk about which is more important, studying or sleeping, and also maybe explain there's some error in this equation, why. Okay, last thing, I already talked you through this actually, but this is kind of like a sample answer. Obviously, you would also have to talk about what's more important, sleeping or studying. But in my sample answer, I also include kind of like, why is there problems? What could be done better in the future, stuff like that. And then also looking at like this variance is kind of low. Sorry, 5%. That's actually not really low. But if it was higher, would it be better? My kind of index of error is pretty high here actually. So even if it was higher, it still would be flagged. So something to look at. And also since it was a 3x3 matrix, it tells you which ones are flagged. And sorry, I keep pressing the button. And all 3 rows are flagged. So every row is having some error until Y is. Okay. As the references, I really want to show you. Here are my references. There's some good things to read actually if you're interested in learning a little bit more just about Cantor in general. This first one had a lot of his work in there, which is really interesting. So hope you enjoy. Good luck on the project, and I'll see you in class.